Lesson 5 video of Unit 12, the probability of independent and dependent events. And today we're going to find the probabilities of independent and dependent events. Now, if they are independent, which means that they do not depend on each other, then the probability of both A and B happening is the probability of A multiplied by the probability of B. However, if they are dependent, which means that if something happens to change the outcome of the other one, the probability that both A and B occur is the probability of A and B is equal to the probability of A multiplied the probability of B given A has already happened. I'll give you an example. Let's say A and B are independent. Find the probability. Okay? The probability of A is 0.3, the probability of B is 0.9. The probability of A and B, since they're independent, I just multiply 0.3 times 0.9. I get 0.27, or 27%. Or in other words, 27 out of 100. Okay, all three of these are equivalent numbers. You can use any one of them. In this one, we know the probability of A is 0.75, probability of B is something, and probability of A and B is 0.15. So we know that 0.15 would have been the product of probability of A multiplied by the probability of B. And I want to know what the probability of B is. So then I just divide. 0.15 divided by 0.75 equals the probability of B. Well, of course, that is 1 over 5, which is equal to 0.20, which is equal to 20%. You can use any one of these. You don't have to use all three, but you can use any one of those forms. Let's say A and B are dependent. That means that it depends on whether B and A happens, okay? So probability of A is 0.1, but the probability that B happens, given that A has already happened, is 0.8. So then I just still multiply them together. 0.1 multiplied by 0.8 is equal to the probability of A and B. So then I'm going to get 0.08, which is 8%, which is 8 over 100. Now, again, if I want to get the probability of A and B, I have to multiply the probability of A together, which I don't know, with the probability of B given that A happened, which is 0.5. Okay, 0.5. I divide to solve 0.25 divided by 0.5 is the probability of A. And then I get 0.5 again, which is 50%, sorry, and then 1/2. There you go. Now, some of you might be curious what I mean by independent and dependent. So I'm just going to try to do another example here. So let's say for this example that I have a bag of marbles. And in this bag of marbles, there are 5 marbles. 3 of them are blue, 2 of them are red. Now, if I asked you, what's the probability that I get a red and a blue if I draw them one at a time? What if I get a red and a blue? I'm going to take 2 out of the bag at once. What's the probability to get a red and a blue? Okay, well, the first one, if I just take one of these, I guess it's all grouped together. Let me ungroup that. Okay, if I take a blue out, the chance of me getting a blue was what? How many blue marbles are in the bag? It was 3 out of 5. So if I pick one, I get it's a 3 out of 5 chance. Now let's say I put the marble back in. What's the chance of it getting a red now? Well, 2 out of 5. Probability of getting a red, blue, multiplied by the probability of getting a red, oops, provided that I put the marble back in the bag, would be 6 out of 10. Or sorry, 25. I had to multiply those together, which ends up being 3. Oh, not 3. I can't divide that. No common factors. 6 out of 25. I'd have to use a calculator quick. I just don't want to do the long division. Getting lazy. 0.24 or 24%. So provided I put the marbles back in, it's independent, right? It's an independent event because I just multiply the probability of them happening. But what happens if I were to pick out of the bag and not put it back in? Well, what's the probability of getting a blue? So in this case, I'm just going to label this as the independent possibility. This is independent. Now let's do the dependent one. Now let's say I don't replace the marble, okay? Let's say I want to get a blue marble and a red marble again. Well, the probability of getting a blue is still the same. It's going to be 3 out of 5, right? Let's say I want to get that blue one. It's 3 out of 5. But let's say I don't put it back into the bag. Now the probability that I get a red given that I've already taken out a blue, is what? Now that I've already taken this one out, how many red marbles do I have? Well, there are 2 red marbles, but how many total are left in the bag? 4. So then I multiply those together. So now if it's dependent, if you don't put the marble back in, I get 6 out of 20, which ends up being 3/10 or 30%, excuse me. So you have a better shot if you don't put the marble back in. And that's the difference between independent and dependent events. Sometimes, if the trials are independent, if I put the marble back in, then the odds are different than if I were to not put that marble back in and do the same experiment. Let's say the game machine claims that 1 in every 15 people win. What is the probability that you win twice in a row? Well, you have to ask yourself, is one trial independent of the next one or dependent? What I mean by that, independent, is that does the first one different than the second one? The odds change. Independent. I had to think about how to spell that. Do the odds change after you take the first one? Now, you get 1 in every 15 people win, and that's just what they say. They claim that 1 in every 15 people win. Now, if you take the crane game or something, like a game machine like this, now let's just do a game machine that doesn't have a crane. Let's just say it has a screen, there's a game that you play. It says that you'll win 1 out of 15 times. 1 every 15 wins. Now, does what happens in the first game you play affect what happens in the second game you play? Not necessarily. Every time a new person comes up to the machine, so let's say the first person comes up and they win. Now, if the next person gets in line, does the fact that the first person win affect this person's chances? I would say no. This is an independent event. What happens to this person does not affect how the other person performs in the game. It's seemingly random, right? They're independent. So to find the probability that you win and win once and win twice is equal to the probability that you win once multiplied by the probability that you win the second time, which in this case is 1 out of 15 times 1 out of 15, if the odds are right. So it's 1 out of 225, not a good chance. 1 out of 225 is a very small number. It's 0.00444. It ends up being just under 0.4%. That's bad chances, 0.4%. All right, let's go to the next slide. You randomly select 2 cards from a standard 52-card deck. Find the probability that the first card is a diamond and the second card is red if you replace the first card before selecting the second. So let's draw another picture. So here's the deck of, oh, that's a bad deck of cards, make it more rectangular. So here's your deck of cards. So in the first trial, you're going to replace the card before selecting the second. So let's say you take 1 card out and you look at it. All right? Then you take that card and put it back in after you're done. What's the probability that you get a diamond and the second time you will get a red card if you put the card back? Well, probably it'd be the probability that you get a diamond multiplied by the probability that you get a red. Now, is this independent or dependent? I would say independent, because if I put the card back, it's like you never even took it out in the first place. What's the odds of getting a diamond in the first place? There are 13 in every suit, so 13 out of 52. I think I like to use 1 out of 4 better than 13 out of 52, though, especially since I'm going to be multiplying. What's the probability of getting a red? Well, exactly half the deck is red. And we're assuming we haven't taken any cards out. So there's still 52 cards in the deck, and half of that would be 26. But again, I like to simplify the fractions before I multiply, because then it's easier to understand. 1 out of 8, that's 0.125, which ends up being 12.5% chance that you get a diamond and then get a red card. But now let's say that you don't put the cards back. Let's say that you have the same deck of cards, and you perform the experiment, but I take 1 card out, like this, and then I take another card out, second card out. Well, in the first card, my chance of getting a diamond was still 13 out of 52, right? So if I got a diamond the first time, that's 13 out of 52. Now, if I take that diamond and keep it out, how many cards are left in the deck? Well, 1 less, 51. Now, how many red cards left in the deck? Was this a red or a black card? This is red, so now there are only 12 red cards left. So 13 times 12, that's going to be a different number. 13 times 12, let me see, that would be 156. No, I'm sorry, forgot the other one. 13 times 12, it's going to be bigger than that. 6, 2, and then next row would be 3, 0, 3, 1, so 6, 5, 156. Okay, I guess I was right. So 156. Maybe I should double check with the calculator just to check. 12 times 13, I'm just second guessing myself. 52 times 51, 2652. All right, let's see what that is as a decimal. 2652. 0.588, so it'd be 0.059 or 5.9%. Not a great chance if I take the cards out. Okay. All right, let's go to the next one. Find the probability of drawing the given cards from a standard 52 card deck, a face card, then a 2 with replacement. That means I'm going to put the cards back in. What's the probability that I get a face and a 2? Is this independent or dependent? Well, it's independent because I put the card back in. There are 12 face cards out of the 52 in the deck. Okay, that means I have 3 out of 13 chance. Okay, if I divide by 4, that's what I did there. Multiplied by the probability to get a 2. There are 4 2s out of the 52 deck. That's 1 out of 13. So I get 3 out of 169. If I reduce that, that's 1 out of, I guess I don't think I can reduce that. Never mind. It's 3 out of 169. Let's just do the division then. So 3 divided by 169. That's going to be a little under 2%. So it's going to be about 0.018 or 1.8% chance. Okay? What do we get? We got heart, then diamond, then another heart. No replacement. So I'm going to take a card out. How many hearts are there in the deck? So probably getting a heart, then diamond, then another heart. Well, the first time I draw a card, how many hearts are there? There are 13, and how many cards are in the deck? 52. Now let's say I picked one out. I'm going to pick maybe the 2 of hearts. So that's the one that comes out. 2 of hearts is out now. Now how many diamonds are left in the deck? Well, I didn't take any diamonds out, so there still should be 13, but there are no longer 52 cards in the deck. I've taken one out. Now let's say that the second card was the ace of diamonds. Being lazy, I don't have to draw a lot, so it's ace of diamonds. Now I want to draw another heart. Well, how many hearts are left if the 2 of hearts is still out? There's only 12 left. And if I've taken the second card out, now there are only 50 cards left in the deck. So to multiply all this together, 13 times 13 is 169. I'm going to multiply that by 12. There are 2,028 possibilities that I get what I want, divided by, this is going to be a big number, 52 times 51 times 50, 132,600. Let's divide that. 2028 divided by 132,600. So it's 0.015 or about 1.5%. That's the odds that I'm going to get what I want. Not great, but it could happen. 1 in 100 times. Here's the last thing we have for today. Let's say the table shows the number of votes in thousands by party affiliation who are expected to vote for Hillary Clinton and Donald Trump in the 2016 presidential election. Number 1, find the probability that a randomly selected person voted for Clinton, and 2, find the probability that a randomly selected Democrat voted for Clinton. So first of all, let's figure out how many people voted in each category. I'm going to figure out how many people voted Democrat, how many people voted Independent, and how many people voted Republican, and how many people voted for Clinton, and how many people voted for Trump. So let's just calculate all these added up together. I'm going to pause the screen and add those up. So you can see the totals now on your screen. So notice that even if I total the Democrats, Republicans, and Independents, I'm just adding these together, plus and plus and plus, and I added these together on the rows, they all add up to having 86,602 or 1,000 people have voted. So it's actually about 86 million people who voted. Now, find the probability that a randomly selected person voted for Clinton. Well, how many people voted for Clinton? Well, 47,403 out of the 86,602 people. So I could find that probability by dividing. But look at the second question. Find the probability that a randomly selected Democrat voted for Clinton. So you have to be a Democrat. Out of the Democrats, 31,378 out of the 33,470 voted for Clinton. So